Welcome to this explainer. Right now, as you're taking in the words on this screen, you aren't just looking at text. Your brain is actually executing a masterpiece of biological computing. For decades, scientists have asked if we could build a machine that genuinely thinks, not just calculates, but actually thinks. And the answer didn't come from science fiction, it came from looking right inside our own heads. So, we're going to dive deep into how artificial intelligence evolved by copying the very architecture inside your brain.
First, just consider the sheer scale of what we're dealing with here. Right now, your brain is firing roughly 100 trillion synaptic events every single second. We're talking 86 billion neurons, each one talking to 10,000 others. It is literally the most sophisticated information processor on Earth, setting a massive biological benchmark. If we wanted to build a thinking machine, well, this staggering number is the level of complexity we had to understand and eventually try to replicate. To demystify deep learning, we're going to zoom all the way out from a single biological cell up to massive models like ChatGPT. Here is our roadmap. We'll start with the biological blueprint, move to the first artificial neuron, uncover how networks actually learn, explore the deep learning revolution, and finish up on the philosophical frontier. All right, section 1, the biological blueprint, the brain's architecture. Let's start at the microscopic level with the human brain's secret design. Neuroscientists discover that despite the brain's overwhelming complexity, a single biological neuron really just follows 3 elegant rules. First, it listens. It receives electrical signals simultaneously through its branching dendrites. It's kind of like a cellular democracy where no single signal dominates. Second, it weighs those signals. Every connection has a strength. Some shout, while others just whisper. And third, it fires. If the sum of all those signals crosses a specific threshold, the neuron fires an electrical pulse down its axon. It's just a simple binary output, on or off. The whole complexity of human consciousness somehow emerges from billions of these tiny on-off switches. Moving on to section 2, the first artificial neuron, the 1957 perceptron. So what happened when scientists tried to recreate those exact biological rules in silicon? What's truly fascinating here is how perfectly the math mirrors the biology. Back in 1957, a psychologist named Frank Rosenblatt built a machine called the perceptron. He essentially created the very first artificial neuron. Instead of biological dendrites, he used mathematical data inputs. Instead of physical synapses, he used mathematical weights to determine the strength of that incoming data. And instead of an axon, it had a simple 0 or 1 output. It would basically multiply each input by its weight, sum them up, add a baseline bias, and if it crossed a threshold, boom, it outputted a 1. The truly revolutionary part? It could actually learn and adjust its own weights based on its mistakes. But the journey from that single artificial neuron to modern AI wasn't exactly a straight line. It was a total roller coaster. After the perceptron's initial promise in '57, mathematicians Minsky and Papert proved in 1969 that a single perceptron couldn't solve basic logic problems, like XOR. It could only draw straight lines through data. And this triggered what's known as the AI winter, which was a massive freeze in funding and interest. It really wasn't until decades later, in 2012, that the AlexNet model sparked a massive deep learning boom. And then 5 years after that, the 2017 transformer architecture fundamentally changed how machines process language altogether. Which brings us to section 3, how networks learn, inside the assembly line. So how exactly do we get out of that AI winter and evolve from a struggling artificial neuron to a system that can learn highly complex patterns? Well, the answer was to team them up. A modern neural network acts a lot like a factory assembly line, organized into distinct layers. First, raw data enters the input layer. Say it's an image. Every single pixel gets its own input neuron. Then the data moves into the hidden layers. We call them hidden because the network develops its own internal language here, discovering patterns totally on its own. The first layer might find edges, the next layer combines those into shapes, and deeper layers assemble those shapes into faces or objects. Finally, the output layer announces the network's final decision, like deciding if that image is a cat or a dog. But remember that big problem from 1969? Without a way to process nonlinear, curved data, stacking all those layers is mathematically useless. To allow the network to learn complex, real-world patterns rather than just straight lines, engineers use something called an activation function. The most famous one is ReLU, or rectified linear unit. The rule here is deceptively simple. If the input is negative, it simply outputs 0. If it's positive, it keeps it unchanged.
When applied across millions of neurons, this tiny little tweak gives networks the absolute superpower to learn almost anything.
But the real magic happens when the network actually makes a mistake. It learns through a repeating 4-step cycle. First, a forward pass where data moves through the network to make a prediction. Second, it measures its loss, basically how wrong it was. Third, it does a backward pass to figure out exactly who is to blame for the error. And fourth, it updates its weights. And it does this millions and millions of times.
Step 2 is absolutely crucial. It relies on a loss function. A super common one is mean squared error. This is just a mathematical formula that quantifies exactly how wrong the network's prediction was compared to the actual answer. The whole goal of the AI is to drive this number down toward 0. The machine uses this specific number to target its exact errors. So how does it actually fix those errors? Enter backpropagation and gradient descent. Using calculus, specifically the chain rule, backpropagation plays a massive blame game. It traces the error backward through every single layer to see exactly which weights caused the mistake. Then, gradient descent adjusts those weights to lower the error. Imagine the loss function as this complex, jagged mountain landscape. Gradient descent is like a marble rolling down that mountain, nudging its way step by step to find the absolute lowest valley where the error is minimized. And modern optimizers like Adam dynamically adjust these steps to efficiently train today's massive models. There is a major trap here, though, and it's called overfitting. Sometimes a network gets so good at the training data that it just memorizes every little quirk and accident in the data. It's exactly like a student cramming for a test by memorizing the practice exam without actually understanding the subject. When they see a new question, they fail catastrophically. To force the network to truly understand the underlying principles, researchers use a genius technique called dropout. During training, they just randomly turn off neurons. It completely prevents the network from relying on memorization and forces it to actually generalize. All right, sections 4, the deep learning revolution, scaling the networks. Having established that basic engine of learning, what happens when we scale these networks and stack these hidden layers incredibly deep? Scaling up gave us incredibly specialized architectures. For images, we use convolutional neural networks, or CNNs. Instead of every neuron looking at the whole image, CNN slides small filters over the image like a visual spotlight, detecting patterns anywhere they appear, which is exactly why your phone can recognize your face instantly. On the flip side, we have transformers, introduced by Google in 2017. Before transformers, AI read language word by word, but transformers process all words simultaneously using a mechanism called self-attention. It figures out deep context by looking at how every single word in a sentence influences every other word. And this brings us to something that genuinely fascinates and, sometimes worries researchers. As these transformer models scale to hundreds of billions of parameters like GPT-3 and GPT-4, they display sudden, unprogrammed skills called emergent abilities. We didn't explicitly train the language model to do arithmetic or write code, but at a certain massive scale, it just suddenly could. These abilities aren't gradual improvements. They appear like a sudden threshold being crossed. And honestly, we still don't fully understand why. Which brings us to section 5, the philosophical frontier, the nature of mind. All this incredible scale asks a macro-level question about consciousness itself. Philosopher John Searle proposed the famous Chinese room argument back in 1980. Imagine a person locked in a room who doesn't speak a single word of Chinese. They receive Chinese symbols through a slot, look them up in a giant rulebook, and pass the correct Chinese response back out. To the outside observer, the person appears to speak fluent Chinese. Searle argues this is exactly what AI does. It manipulates symbols according to mathematical rules, producing outputs that give the illusion of understanding. But inside, there is no actual comprehension. There's nobody home. Which leaves us with this ultimate question. As billions of artificial neurons successfully combine to write code, translate languages, and even help diagnose cancer, is it all just pure, elegant math? Or, as these models generalize, handle novel situations, and mimic reasoning, does the machine actually understand? Neuroscientists call the human experience the hard problem of consciousness. We don't have an answer for why the human brain feels things, and we certainly don't have one for AI yet. So as you process all of this with your own biological neural network, ask yourself, at what point does perfectly imitated intelligence become real intelligence?